Hello friends, welcome to my channel. So today I'm going to start a new series for algorithmic problem solving, and for that I'll begin with bit manipulation techniques in Python. So bit manipulation techniques is very useful in solving various algorithmic problems on various coding platforms like LeetCode, HackerRank, HackerEarth. So um, yeah, today we will see how various bit manipulation techniques and various uh, operations that can be performed on binary numbers. Okay, so let's begin. Okay, so I'm going to use Jupyter Notebook to explain all the concepts of bit manipulation in Python. Okay, let's begin. So Python provides, in order to represent a binary string of a number, Python provides a bin function. So if you use bin function and give it any number, it will give you the string representation of the binary of that number. Okay, so here I am printing the number and as well as its binary. So you can see that number is this and its binary representation is 1010. 0b represents the binary number. Okay, now another useful um, bitwise operation is AND operation. So what are the properties of AND operation? If you AND or any binary bit with 1, okay, in binary, it keeps the original as it is. Okay, so 1 and 1 remains 1, 0 and 1 remains 0. Okay, if you AND any binary number with 0 bit, then that original number is changed to 0. So basically, okay, so 1 and 0 is 0, 0 and 0 is 0. Okay, so below I have printed all the results of binary AND operation. Okay, similarly there is a bitwise OR operation. Okay, so in case of OR, if you OR any binary bit with 1, the result becomes 1. Okay, if you or any binary operation with 0, the result is same as the original binary number. Okay, so 1 or 1 is 1, 0 or 1 is 1, 1 or 1 is 1, 0 or 0 is 0. So basically if any of the bit of the two binary bit is 1, the resultant bit is 1. Okay, so here we can see that it is as expected. Okay, third binary operation is logical shift operation. So if you, so let's say there's a number 7. Okay, its binary is this 0111, and let's say if I shift this binary, left shift this binary by 2 bits. Okay, so my result becomes 0 1 1 1 0 0. So basically it adds two zeros to the right. So this is my left shift operation, where we shift the original binary number to the left. Okay, so when I print it, when I print this number after shift, the result is 28 for 7. So what it means is basically left shift operation is basically nothing but a multiplication operation of the original integer. So since I'm left shifting this 7 by 2 bits, okay, two zeros are added to this original binary number. So if we convert this binary to decimal, the result is 28. So it's basically multiplying x with 2 to the power 2, because I have used 2 bit. If I have used 3 bit, then it would have been multiplying x, basically 7 with 2 to the power 3. Okay, so it's a multiplication operation can be performed with left shift operation. Okay, similarly there's a right shift operation. So right shift, right shift is reverse of binary left shift. So when we right shift any binary number, so let's say I have number 8, this is its binary representation. If I right shift this binary number by 2 bits, okay, so essentially I'm doing is I'm dividing y, basically I'm dividing I'm dividing 8 here, okay, with 2 to the power n. So basically when I right shift this 8 by 1 bit, so original was this, okay, binary. After right shift it becomes this 0100. So it adds 10 to the left and removes one, basically binary bit from the right. So basically I divided this 8 by 1, by 2, basically 2 to the power 1, because I have right shifted it by 1. When I print this number, the result is same, basically, since we have right shifted it. So 8 is divided by 2, result is 4, and this is its binary representation. Okay, one of the most crucial binary operation is XOR, and through XOR, many problems can be solved because it is very useful for problem solving as well as in computer science. So what is XOR? So XOR says that if you XOR two numbers, so in those two numbers, if both the bits are 1, if both the bits are same, then result becomes 0. If any of the bit of those two bits is different, then result is 1. Okay, in another words, if you XOR any bit, whether it's a 1 or 0, with 1, okay, the original bit is inverted. Okay, toggled. So it was 1. If I XOR 1 with 1, it becomes 0. If I XOR 0 with 1, it becomes 1. Okay, and if I XOR any binary number with 0, okay, the original bit remains same. So if I XOR 1 with 0, it remains 1. If I XOR 0 with 0, um, it remains 0. Okay, so anyways, if any of the two bits is if any of the two bits are same, the result is 0. If any of the two bits are different, the result is 1. Okay, either this, or if you XOR any number with 1, the result is it toggles the original number. If you XOR with 0, the original number remains same. Okay, so this is very useful property. Okay, let's understand it further. So let's say I have one number as 7, its binary representation is 0 1 1 1. I have another number as 5, its binary representation is 0 1 0 1. If I XOR these two, okay, the result becomes 0 0 1 0, because here 1 1 is same, so 0 1 0 1 1 1 0 and 1 0 0 0. Okay, so as you can see, result becomes 2 with its binary. So this is the binary of 2 basically. Okay, one another important property of XOR operation is, if you XOR, let's say, x and y, and result is z, if you XOR again any of the original numbers with the result, it gives you another, uh, basically the original another number. Okay, so here I am XORing x with y, it gives me z. If I XOR y with z, it will give me x, and if I XOR z with x, it will give me y. So you see, this is very useful. So basically, um, if you can predict, so this is if you want to swap a number x with y, so this is very useful property of XOR. Through this, you can swap x with y. Okay, in programming. So yeah, as you see, I have XORed x with the result again, which is z, so it will give me y again. Okay, so as you can see, it's again giving me the original number 5. Okay, another property of XOR is, if you XOR any number with 0, the result is that number itself. This is called as identity property. So if I XOR x with 0, the result will remain x, original x. So original x was 7. So as you can see, I'm printing this x and its binary, okay, which is 7. Fourth property is, if you XOR um, a number with itself, then the result is 0. This is called a self inverse property. So let's say I'm XORing x with x itself, so the result will be 0. Okay, this is another useful property of XOR. You can actually see, write down x as binary number, and you can, if you XOR with x itself, it will eventually give you result 0. Okay, so this is XOR operation in Python you can perform. So XOR is performed by using this cap operator, okay, that you can use. So if I execute this block, it gives me the result we discussed. Okay, now another bit binary operation is ones complement. Okay, so if you call it ones complement, or you call it inversion of all the bits of the original number. So if you want to invert all the binary bits of the original number, you can use tilde sign in binary in Python. That will give you the original number but all the bits inverted. Okay, so let's say I have 7, its binary representation in 8-bit binary is this. Okay, if I invert this, it inverts all the bits of this binary to this. Okay, and if I print x, y, and binary of y, it gives me original number the inverted number. So basically why this is minus 8 is basically in 8-bit binary the MSB represents uh, sign of the number. So if it's 1 it means it's a negative number. So in one's complement, basically this is treated as minus 8. Okay, but it's actually inversion of all the bits. Okay. Yeah, and I printed this number, which is why, as you can see, we already have four numbers, so it gives me this, but negative. Why? Because its MSB is 1. Okay, so this is one's complement, or basically inversion of all the bits. Okay, one another important binary operation is called 2's complement. So basically 2's complement is used to represent signed numbers. Okay, it can be positive, negative, or neutral. If any kind of signed number you want to represent, it is represented in the computer system with 2's complement. Okay, so in 2's complement arithmetic, positive numbers are represented with normal binary number, where, as I mentioned, right, if MSB is 0 it means its number is positive. If MSB is 1 it means the number is negative. So negative numbers are represented with MSB as 1. Okay, let's understand this. So basically MSB bit determines the sign of the number. 1 means negative and 0 means positive. So if I, so what is 2's binary in 8-bit binary number? So this is the binary number of the 2. And if I want to represent minus 2, so how it is represented is basically we take one's complement of the uh, absolute value of 2. Okay, its one's complement is nothing but its inversion. Okay, so this is the one's complement of the 2 and we add 1. So one's complement plus 1 gives me 2's complement of the minus 2 number. So minus 2 is represented in computer as this. Okay, so what is a simple way to find out 2's complement is basically, so if let's say I have 8-bit number, so through 8-bit, okay, I can represent 0 to 255, basically 2 to the 2 to power 8, which is 256 numbers, which is basically 0 to 255. Now this I can represent if I use unsigned 8-bit number, but if I want to use signed number, then I can only represent positive numbers from 0 to 127 and negative number from minus 1 to minus 128 using 2's complement arithmetic. Okay, so you see, right, so simple way to find 2's complement is basically you first figure out 2 to the power n. N is basically number of bits used to represent a number, and you minus the original number from it. So okay, so if you want to figure out 2's complement of minus 5 using 8-bit, it will be 2 to power 8 minus 5, that is 2 to power 8 is 256, and if you remove minus 5 it will be, sorry, 251. Okay, so 251, um, 251 decimal, okay, in using 2's complement represents minus 5. Okay, so let's understand it further. So let's say I have the number 5. Okay, its binary is this. Okay, it's one's complement, basically inversion of all these bits is this, and if I add plus 1 here it gives me this. Okay, so this binary, if you convert it to decimal, it will give you 251. That means that this particular binary number represents minus 5. Okay, in 8-bit um, representation. Okay, if you want to see 2's complement of the number in Python, then we will have to do some operation. So what we do, so basically this is my original number, okay, which is 5, and I want to see minus 5. Basically I want to see the 2's complement of the minus 5 number. So what I will do, I have the original number 5. I x, so okay, first understand this. So I basically left shift 1 by 8-bit. It will give me binary of 256. I minus 1 from that, so it will give me decimal number 255. So this will be, so 255's binary number will be all ones. Okay, if I XOR all ones with 1, as we see, right, while discussing XOR, if I XOR any number with 1, okay, uh, it reverses all the bits of the original number. So okay, it will give me ones complement. Okay, so basically this is the binary of 5. I XOR it with all ones here. Okay, so it will give me this number. Okay, so it gives me this number. Okay, this is ones complement. So if I print y here, it is 250. Okay, this is just a ones complement, we have not yet added plus 1 here. Now if I add plus 1 to this y, it gives me 2's complement of minus 5. So you see, this is the 2's complement of x, basically representing minus 5 means this original ones complement plus I added 1, so it gives me 2's complement of minus 5. If I print this number, okay, this is its representation in binary, and this is 251. So this is basically a decimal number in binary, but actually this is this representation is, if you, this representation is nothing but uh, minus 5. Okay, minus, this is how minus 5 is represented in system, because here MSB bit is 1. Okay, so this is just to show 2's complement binary. If you just want to know the result of 2's complement without knowing its binary representation, what you can do is you can simply invert the original number and you can add plus 1. Okay, using this you will just get uh, the, using this you will just get the 2's complement representation of the original number x. Okay, so if I print y here, x, y and minus 5, so my original x was 5. Okay, so y, what y is doing, y is doing 1's complement plus 1. Okay, so it will be, so it, so original number x will be represented in basically negative value of the original x uh, uh, is done using 1's complement plus 1. So y here is giving minus 5. Okay, if I print binary of y, then this is minus 101. Okay, this is just giving me the result of 2's complement. I'm not printing a binary number. Okay, another useful bitwise operation is, if you want to, let's say, get ith bit, that is you want to determine what if what is the let's say third bit of 5, whether it is set to 1 or 0. How we can figure that out? Let's say I have x as 5, so how that I can figure it out? Basically using AND operation. So what I will do, if I want to check second bit starting from 0 uh, of the, of this particular binary number, which is binary of 5. Okay, I'm left shifting 1 by 2. Okay, which will basically, which gives me 0 1 0 0. Okay, and I end with 1. Okay, so basically I am ending this binary with this binary number. So you see here, right, 1 1. So if result becomes non-negative, it means that second bit of 5 is uh, 1. Okay, if result is 0, then it is 0, but if it gives me result as 1, basically you, if you do end with, end of this with this, right, it gives you 0 1 0 0. So it's non 0, so it means the the second bit of 5 is 1. Okay, another method is, you can do right shift of original number and you can end with 1. So if you want to see if second bit of x is 1, is 1 or 0, you can right shift that number with 2 and you can end with 1. And if result is 0, it means that second bit is uh, if result is non-zero, it means second bit of x is non-zero, otherwise it is 1. Okay, so basically we are doing this particular operation, and between these two, and result will be 1. So this result is non-zero, so it means the second bit of x is non-zero. Okay, if you want to set any binary, if you want to set any bit of a number, the set operation can be performed using OR operator. Okay, so let's say I have binary of 5 as 0101. I want to set first bit of this, basically this particular bit, to 1. How I can do is, I left shift 1 by that number of bits. So I want to set first bit, this is 0th bit, this is first bit 0. So I want to, I will left shift 1 by 1. Okay, it gives me a value as 0010, and I OR it with x basically. Okay, so I am, and as we have seen the OR operation, bitwise OR operator, if any of the bit is 1, the result is 1. So basically this will set first bit of x to 1. Okay, I have printed the binary here. As you can see, result 111. That means that it was 101. I'm setting first bit this 0 to 1, so result gives me 111. If I want to let's say set second bit of binary to 0, this is another way. So you can do this way also, x, and so basically you left shift 1 with 2 bits. Okay, then you reverse it. Okay, and if you, and after reverse, if you end it with x, it will set that particular number to basically 0. Okay, so this is to set it to 1, this is to set it to 0. If I printed the binary of z, it is giving me 1 basically. So basically I am here, I'm setting this first one, what was that, this first one here to 0, so result remains only 1. That's why it's giving me only 1. Okay, another useful bitwise operation is toggling. So basically, if you want to toggle ith bit of a particular number in Python, you can do this like this. I have x as 7, its binary is 0111. If I want to toggle second bit of this binary, so what I will do, I left shift 1 by 2 basically, because I want to toggle second bit, and if I XOR it with original number, it will toggle this second bit. So as you see, I printed the binary of y, so the result is 101. So this operation can be, left shift and XOR operation can be used to toggle a particular bit of any number. Okay, now let's understand three more operations. So basically, let's say there is a requirement to clear bits in an original number. Okay, so before that, let's understand binary subtraction. So if you subtract 1 from any number, okay, the result, so here if I'm subtracting from 8, I'm subtracting 1, the result gives me 7. So if you understand it properly, what this subtraction gives me is basically, if I subtract 1 from any number, it toggles the first ones from right. Okay, and all its right numbers. So it has toggled the 1 to 0, and it has toggled all its right number to their um, another bits. So here it was 1, so it is 0, and all these three zeros are toggled to 111. Okay, now let's say I have x as 14, its binary is 1110, and uh, I want to clear all the right bits of this binary number, okay, to 0 until second number, basically second bit. Okay, so what I will do, I will create a mask, I will left shift 1 by 2. Okay, and I will uh, do -1. So what it's giving me is, this is the left shift of 1. Okay, if I do -1 here, as I said, it inverts all the rightmost bits till the first one, so all these three bits are inverted. Okay, now using this mask, if I end my mask with the original number 14, okay, what it will do, it will clear all the bits from MSB to ith bit. So if I want to clear all the bits from the most uh, significant bit till the second bit, I want to clear all these bits, I can do like this. Okay, I left shift 1 by uh, number of bits, then -1, it gives me this, and if I end with original number, it clears all the bits from MSB to ith bit. Okay, so here um, yeah, here its result will be 0010. Okay, if I end with this and this, its result is this. Okay, if you want to, now here we have cleared all the bits from MSB to the ith bit. If you want to clear all the bits from LSB to the ith bit, just same operation, but just invert the mask and end it with x, so it will invert all the bits starting from the left significant bit till the ith bit. Okay, here I have executed this number, so you can see this result is 1100. So here original value was this. We have cleared all the LSB and it's and the uh, basically till ith bit, I is 2. Okay, so we clear all these bits here. Okay, another operation is if I want to get the lowest set bit in binary. If I want to get the lowest set bit in binary, so let's say I have one number as 6, its binary is 0110. Here you want the result to be 0010 because I want to get the lowest set bit. Okay, so what I will do, I will AND the original number with its negative number. So basically minus x is nothing but 2's complement of x, that is 1's complement plus 1. So minus 1 is represented like this. If I AND this number with the original number and if I print its binary, it gives me 10. Okay, I AND this with this, it gives me binary of 1 is 10, that is this one. Okay, so I want to, here I have basically zeroed all the numbers except the lowest set bit. So basically the value when all the bits are zeroed and lowest bit is set, it gives me this number. Okay, the last operation is if you want to clear the lowest set bit. Basically its application is, let's say if you want to count number of bits are set in the original number, you can perform this particular operation. So if you want to clear the lowest set bit and keep on doing it, it will give you number of set bits. Okay, so let's say I have x as 6, its binary is 0110. Okay, if I AND this number with x minus 1, okay, then it will clear the lowest set bit. So original was this. If I AND that number with x minus 1, okay, as we have seen the property of x minus 1, if I do minus 1, then it basically inverts all the LSB till first one. So if I AND that particular thing here, what we are doing is essentially is this 0110, ending it with 0101. Okay, I'm ending it with this. So it gives me its result is basically 0100. As you can see, it's printing the correct results. Okay, so we have learned 14 bitwise operations in Python. Those are very useful while solving various problems on for interviews or basically in colleges for various computer science applications. I hope this helps, and let me know if something is not clear. I will try to explain it again. Okay, thank you.